Yay, it works. Okay, so I'm going to tell you about the multi-messenger searches of gravitational waves and high-energy neutrino sources. So to start, I would like to tell you my own definition, or my favorite definition of multi-messenger astrophysics. So it's basically using the four fundamental forces of nature in order to study the astrophysical sources and transient universe, or basically the most violent phenomena in the universe. So these forces are electromagnetic, weak, strong, and gravity. So we actually search for these sources that emit at least in 2 cosmic messenger channels. It doesn't have to be all the cosmic messengers. So in this picture, you can see the multi-messengers. So this is basically, or the cosmic messengers. So these are cosmic rays here. We have neutrinos, gamma rays, electromagnetic emission, any type of photons, and then gravitational waves. So the good news is that all of these cosmic messengers are actually discovered or detected. The next good news is that we have been able to observe a few multi-messenger sources in the universe. So in the case of neutrinos and photons, or electromagnetic counterparts, we have been able to detect 3 sources so far. So one is our own sun. Sun emits a lot of light, as we know, and billions of neutrinos every second. So that's basically the first multi-messenger source we ever could detect. The next one is supernova 1987A, which also detected, we detected neutrinos and photons from that. And then the third one is the neutrino event that we detected in 2017 with Icecube Neutrino Observatory, and we called it Icecube 170922A, and it was actually in coincidence with a flaring blazar. Blazar is actually a supermassive black hole that has accreting matter around it and producing jets, that if one of these jets is actually pointing towards us, then we call it a blazar. So let me show you a movie that actually we made after the detection of this high-energy neutrino. And this movie shows basically these neutrinos and photons are generated and emitted from the blazar, the source, the astrophysical source, and move all the way to the Earth to get detected in our Icecube detector. So this is the movie. So this is the constellation Orion, and this is the location of our supermassive black hole. It sends out all these photons and neutrinos. Photons are shown in purple. Neutrinos are shown in white. And they travel, neutrinos specifically, travel all the way without being attenuated or impeded to the Earth, and goes into the ground and moves through the matter that we see in the ground, specifically goes to the South Pole. And there we have a lot of ice molecules. And it doesn't hit any of those until it reaches one of these ice molecules, interacts, and make a lot of secondary particles, as well as these beautiful cone of blue light. We call it Cherenkov cone. And then this is the Icecube detector. So we have a lot of sensors, and this produced light will hit and turn on all of our sensors. So we detect the neutrino, and we can point back to its direction. So after we detected this neutrino, we reconstructed its energy and direction in real time and sent out the information to astrophysical community. And they performed follow-up observations. So based on this animation here, you see all the follow-up detections of this event based on the public telegrams. First, we had observations from Swift, Fermi, and then you can see a lot of like Cherenkov gamma ray telescopes or optical telescopes that they all reported that there is the source. And Fermi was the first telescope actually reported that this source was in a flaring state. So there was a lot of electromagnetic emission. And this was basically the first multi-messenger event involving neutrinos that we could follow up in real time. And after, of course, supernova 1987, but this was very huge campaign, and it resulted in the first and only 3 sigma high-energy neutrino source association, indicated that blazars may be sources of high-energy neutrinos. So the next good news is that we have detected gravitational waves or sources that emit gravitational waves and gamma rays. So you all know about the gravitational wave events because you heard interesting talks before about that, so I'm not going into the details of this one. But now the question is, are there astrophysical sources that can actually produce gravitational waves and emit high-energy neutrinos? Can we look for something like this? And if we found something like that, are there going to be electromagnetic counterparts to it? So here we actually look for a low latency algorithm for multi-messenger astrophysics, or LLaMA. And this is the search that we do at Columbia University. We have 3 brilliant graduate students, Doa Visky, Rainer Corley, and Stefan Countryman. And you already met Zhuja and Sabi, who are the pioneer of this search, and Imre Bartos, and of course the LLaMA. So we search for these sources in real time, and we have not seen any astrophysical sources yet that emit in both of these cosmic messengers, but there are candidate sources. Several sources proposed, such as binary neutron-star merger or neutron-star black hole mergers, or core collapse supernovae, gamma ray bursts, soft gamma repeaters, and so on. The most promising of these is the short gamma ray bursts from their progenitors, binary neutron-star mergers. And we definitely need to have some relativistic outflows to be able to produce or have hadronic interactions and produce the high-energy neutrinos. And of course, we always have to be open-minded and look for known sources, unknown sources that we would like to discover. So there are advantages of doing a joint gravitational wave high-energy neutrino real-time search. One advantage, or the main advantage, is that, as you know, the gravitational wave sky area is very large. And here you can see a simulated event with 1 detector sky map, the 2 detector and 3 detectors, LIGO, Virgo, and 2 LIGO detectors and Virgo. And you can see that even in the case of 3 detectors, still the sky area could be large, could be a few degrees, square degrees. So on the other hand, neutrinos have a better angular resolution, about ½ a degree in most of the cases, so it can localize the location of the event much better, and it will be very helpful for the electromagnetic follow-up observations. The other thing that I think is very important, we are not actually working on that right now, but we need to start this, is the subthreshold search. Meaning that when I say subthreshold, it means that the individual data stream are not significant, like not very, very significant, but the point is when we combine them, when we combine 2 messengers from 2 different observatories, then the joint search will increase the sensitivity of the individual data. So that could help us to actually also find some events and ask telescopes to point to that direction, and it has a lot of discovery potential. And as we go, and as you know, there are a lot of gravitational wave events, and it will be increased in the following years. So it is very important to automate things, because then if we do not, then we will have analysis backlogs, and we cannot control all of these searches. So for our search, we get gravitational waves from LIGO and Virgo, and the neutrinos from the Icecube observatory. And as Sabi already mentioned, Icecube observatory is at the South Pole, is a gigaton detector. It's a great experiment. We have drilled down about 2.5 kilometers and inserted all of our sensors or digital optical modules in 86 strings here. There are more than 5,000 of these sensors in ice, and we detect high-energy neutrinos whenever they make interactions in ice. So this is the data stream that we use in the LLaMA-GWEN search. So we get our data from the public alerts of LIGO at this moment, and these are from the GRACE-DB. We also get our Icecube triggers from a stream called Gamma Ray Follow-up, and these are actually through-going muon tracks, so they're very long tracks. It's easy to point back to their location. And then we run the analysis. We produce joint sky map and calculate the significance of these alerts, and then prepare a GCN circular draft. This is the timeline of our pipeline. So we have to wait for 500 seconds because the way we have defined our search is in a time window of 1,000 seconds centered on the gravitational wave alert time. So definitely we have to wait 500 seconds to collect all of these Icecube neutrinos. And then the rest of the things is pretty fast. So it's in less than a few seconds, actually, we can run the analysis and produce the plots and upload the results. Then we define a test of statistics that is actually incorporating all the astrophysical priors and detector characteristics. And we define whether any gravitational wave or high-energy neutrino alert is a real signal, meaning that the gravitational wave and neutrino both are from the astrophysical signal. And there are two other options. We can have chance coincidence of a background gravitational wave and a background neutrino. In the case of public alerts, because we assume that all the gravitational waves are actually signals, so this is 0. And then we also could get chance coincidence of astrophysical gravitational wave and background neutrino, or vice versa in the case of subthreshold theta. Then we calculate our p-values using the Bayesian odds ratio or Bayes factor, simply by p signal over p null plus p coincidence. The difficulty here is to define all these priors very carefully, which our brilliant graduate students do. So this is an example of our search, and this is basically our internal Icecube analysis. So the LIGO map is, of course, public, but these types of maps is what we use to help our eyes and basically calculate all the information. In case of discovery, or in case of finding a significant correlated event, we actually will publish this event. So we publish the time difference, direction, angular error, and number of correlated neutrinos with the gravitational wave event, and the p-values. So we send out the GCN circular, and here I want to point out that currently we test two different hypotheses in Icecube, and I only talked about one of them, which is our Columbia search, and the other one is done by a group of researchers in University of Wisconsin-Madison. So in the GCN circulars, we actually report the p-values of both of these analyses, or we plan to report it from now on, both of these analyses. And we would have possible revisions and retractions due to improved GW or high-energy neutrino localizations, or in case of a retraction of one of the input triggers. At the end of my talk, I would like to emphasize on the importance of electromagnetic follow-up of these alerts. The reason is we really need electromagnetic information to understand the source and the mechanisms that produce the neutrinos, as well as understanding the gravitational wave sources better, like, for example, constraining equation of state of neutron stars that you heard in one of the previous talks by Sean, and then, of course, understanding the jet mechanisms, hadronic interactions, leptonic interactions, all these particle physics studies. So one of the programs that we have already been approved is by Swift X-ray telescope and ultraviolet optical telescope. So we have 4 highest priority target of opportunities. So as soon as there is one low p-value, high significant alert, we will send it to Swift for follow-up. And we also have, there are also interests in ZTF optical telescope, and we also hope that LSSD will follow up these kinds of alerts, because LSSD will also be very important in even finding the early optical counterparts to these alerts, and it will help us to have a lot of science opportunities, estimating cosmological parameters, and studying the R processes, and as I said, the particle production mechanisms and jet physics, and collapse of massive stars, and so on. So stay tuned, and we hopefully will get one of these alerts very soon, and we make more discoveries. Thank you.